if you would, could you draw in this picture? Go ahead. I'm going to wait a moment while you do that. I'll talk while you're doing it. Here I have a B field that is pointing into the paper. I have a loop. It's the same loop. In the first case, there's an external force pulling it into the magnetic field. In the middle, there's no external force, and it's just sitting there. And in the third, it's actually being pulled out of the magnetic field. You know what? I think that when it's all the way in, we're still going to have an external force on it. The same external force. Let's draw that in. We'll keep it moving. Okay. So, what's going to happen? Let's break it down. In the first situation, all the way to the left, I'll label it A. During A, I am going to say that the flux increases. Therefore, the B field opposes the change in the flux. So the B field produced in the loop is going to be the opposite direction, or out of the paper. So, ready? The B field is out of the paper. Get your right hand out. Good. Fingers inside the loop. B field coming out at you. While it is being pulled into the B field, the current is going to be counterclockwise. For B, even though the wire is moving, there's actually no change in the flux. Once it is completely in or completely out of the magnetic field, the flux doesn't change. Therefore, if there's no change in flux, there is no current. All right, if you just woke up, that's a big one. If there's no change in flux, there's going to be no current. Lastly, in part C, as that external force is pulling it out, what's going to happen to the flux? Well, the flux is going to decrease. If the flux decreases, the B field is going to be in the same direction. Therefore, the B field induced in the loop is going to be into the paper. So now, I get my loop, I put my hand into the loop, and I put it on each side. I usually only do 3 sides because I can't quite spin all the way around. And what I see is the current is going to be clockwise. Yeah, did you get that? All right, cool, good. Now, here's the thing. While there is an external force on that and current is flowing, do you know what acts opposite this motion? Yeah, when one object exerts a force on a second object exerts an equal and opposite force on the first. And here's the thing. When there's current traveling through the wire, in a magnetic field, there's a force on it. The force that opposes that motion is equal to BIL. So first thing, there has to be an external force to pull the loop into the field. Otherwise, it won't go into the field. And then as that external force is acting on it, there is a B field force, or a force from the B field, acting in the opposite direction. Now, in the first case, it's going to be acting to the left. In case B, when it's in the middle, yeah, no force at all because there's no current. And then lastly, the force is again going to act opposite the external force. So it's going to be acting back against the motion. Now, therefore, we can do a little sum of the forces here. I gotta love it. The sum of the forces causes the mass to accelerate, except when it don't, except when it's traveling at a constant speed. So I can see here that if I pull harder, the magnetic field is going to pull harder back. If I pull with less force on the external, it'll go slower, and there'll be less force from the magnetic field holding it back. The current would become less. Oh, see how it's all tied together? So, by definition, the external force, in order to get it to travel at a constant speed, if we say right is positive, the force of the B field is negative, those two forces are going to be equal. Oh yeah, you can see how we can get some cool problems. So I hope you wrote that formula down. All right, moving on. Example number 4. Still hanging in there? Let's try this one. In fact, I'm going to ask you to push pause if you know what's going on and do this one yourself. Ah, you didn't push pause. Come on, push pause. Good. All right, did you do it? Awesome. Let's see if my explanation is correct and it agrees with yours. Here I have the south end of a magnet. Now, the south end of a magnet is going to create a magnetic field that points towards it. So towards the south end. You just have to know that. If you don't know that, you are totally stuck on these problems. Out of the north and into the south. Now, that's the direction of the magnetic field. Now, it's being pulled away. Because it's being pulled away, that indicates to me that the change in flux is decreasing. Sometimes I just draw an arrow pointing down. Means getting less, right? The change in flux decreases. Therefore, the B field is in the same direction because Lenz's law says that the induced B field opposes the change in flux. The induced B field opposes the change in the flux. So that induced B field is also going to be in the same direction. So now I take out my right hand. No, this one, right hand. Put it in the loop and figure out the direction of the current. Go ahead. In your mind, don't look at my picture because it's opposite thanks to Zoom. Yeah. Anybody else get clockwise? The same direction a clock goes. All right. If you didn't get it, maybe I'm wrong. Hope not. We'll find out in class. Next, go ahead and draw this one. The B field is pointing out of the paper, and the loop is being pulled out. Because it's being pulled out, the change in the flux is decreasing. Therefore, the B field that's induced is the same. Good. So if the B field induced is out of, I then take my right hand. Go ahead, you got it. I kind of move. So I'm touching all different parts of the wire on my palm. My palm is inside, not outside, inside the loop. And again, I have counterclockwise. Good. Let's try one more. One more. Draw it. Go ahead. Draw it. So that's the south end of a magnet being pulled away from a loop. Now it's difficult to understand the perspective. Now this loop, this edge is the front edge, and this one is the back edge of the loop. It's like this. I know that because of the way the line is drawn through it. Some of you artistically challenged people are going to have a little trouble with that, but not you guys. Now, if you want, push pause. Do it. Push pause and get it yourself. Go ahead. I've got this. This is the north end of a magnet, because that's how magnets work. I have field lines that then are pointing out of the north, but it's getting farther away, so the change in the flux decreases. So the B field has got to be in the same direction. That means that the B field is pointing this way. So I take my hand, I get it inside the loop, I put my palm against the wire, whoop, 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 and my thumb is going this way, clockwise. Now, I know that if you watch my video, it's going to mess you, not the whole video, come on, this is beautiful work. But if you watch me personally in the corner, it's opposite, the camera flips it. So do it yourself, put your hand in that loop, put your palm against the wire, and see which direction your thumb is going. That's the key. So I end up with an answer that is clockwise. All right, now, did you get all that? I don't know. Are you still awake? I don't know that either. But what I do know is we're well on our way to understanding one of the trickier concepts of the entire year, which is Lenz's law, used to determine the direction of the current with Faraday's laws problem. Gosh, there's a lot of words. Hope you guys got this. We'll practice a lot. Don't worry. You can also always go back and check this out. It's always simple. All right. Thanks for your patience. You guys are hanging in there. See you in a bit.